This is the second half of the Chapter 2 presentation for GD&T. First of all, we're going to talk about geometric tolerancing symbols. So what is a tolerance? So a tolerance defines the allowable variation on a part size, part feature, or part form. So variation occurs in every part. Parts cannot be manufactured perfectly. Therefore, we need tolerances to be defined to specify the allowable variation for any size or feature or orientation of a part. So each tolerancing symbol shape reflects its purpose. So geometrics, we are talking about four things in geometrics. We can talk about what a form tolerance is. There's four categories: form tolerance, an orientation tolerance, profile tolerance, runout tolerances, and then locational tolerances. These are the four categories of geometric tolerances. The symbols that we're going to use for those categories are shown in this slide right here. So for form, we have straightness, and then here's the symbol we use for straightness. We have flatness, circularity, and cylindricity. Okay, and this is a handy table. We're going to be referring back to this, but as we go further in explanations, we're going to find that we never use a datum for these features. There's two types of profile tolerances: profile of a line and profile of surface. Here are their symbols. There's three types of orientation tolerances in geometrics: angularity, perpendicularity, and then parallelism. And then for location, there is position, concentricity, and symmetry. Concentricity and symmetry are not very useful. When we start talking about location, we'll talk about positional tolerances mostly. Concentricity and symmetry are not used very much anymore. And then the last basic category of geometric tolerancing is runout. And here's the symbol for circular runout, and then here's the symbol for total runout. Okay, so these are the form categories. I kind of went over it in the table: straightness, circularity, flatness, and cylindricity. These are the orientation category symbols: perpendicularity, angularity, and parallelism. These are the profile category symbols: line profile and surface profile. Here are the runout category symbols: circular and total. And finally, here is the location tolerance symbols: position, symmetry, and then concentricity. Okay, modifiers. We're going to talk a lot about modifiers. I just want to introduce the concept here, but we're going to be talking about modifiers a lot in this class. So don't let this confuse you too much right now. So modifiers used in datum feature reference section of a feature control frame. They can be the least material boundary, or the maximum material boundary, or regardless of material boundary. And these modifiers are used to help define the function of the part and help to refine the tolerances for the geometric controls that we're going to be using. Now, how are geometric controls applied to a drawing? The geometric controls are applied using a feature control frame. Okay, here is a symbol of a feature control frame. This is a sample right here. It's a straightness tolerance of 0.007, or I would say 7 thousandths. Okay, so this is the feature control frame. Here's the geometric characteristic that defines the tolerance, and here's the numerical value of the tolerance. Okay, now this one here is a little bit more complex. We have a positional tolerance here, and our tolerance value is 29 thousandths, and the diametral symbol in this case defines the shape of the tolerance zone. This M here is a modifier. It means maximum material condition. We'll talk about that as we go on in this course. And all I'm really trying to do with this is introduce you to what a feature control frame is and what are its elements. Okay, And then these are datum references, datum A, datum B with a modifier, and then datum C. Okay, and then what we have here on the lower line is a perpendicularity tolerance. So we have a perpendicularity within a diametral shaped tolerance zone. The size of that tolerance zone is 10 thousandths, 0.010. There's a modifier on it and then a datum reference. So the basic components of your feature control frame are geometric tolerance symbol, tolerance, and datums. Okay, and so that's the point of this one. I'm not trying to get too far ahead of myself. I'm just trying to show you the components of a feature control frame. Now here's how a feature control frame is applied. Okay, there's several ways to do it. If you're doing it to a surface, you can put a line here with a dot. So what this says is that I'm applying this flatness tolerance to this surface right here. Okay, up here I'm applying the flatness tolerance to this surface. Or the other way I can do that is with an extension line from that surface and then put the feature control frame below it. I can put it on this side, I can put it on this side, I can put it on the upper side of this, or I can have an arrow pointing to the surface. That's how you would apply a feature control frame for flatness. Now what we're having here, is a slot, and it has a positional tolerance. Okay, and I can apply that by either placing the feature control frame beneath the dimension that defines the size of the slot, or I can put it as like a leader to the extension line on the other side. There's two ways I can do that. And then this is how you would do that same thing in a model. So that is how feature control frames are applied. Now, like I said before, in this picture we've got a datum identification here. Datum identification. Datum features are the surfaces and or features of size that are used to establish a theoretically perfect frame of reference from which the geometric tolerances are applied. So, datum feature symbol applications, that would be a datum feature symbol or a datum target symbol. We'll talk about those in a little bit. Or a datum reference frame. Okay, so again, this chapter is meant to be an introduction to this material. We are going to talk about datums in detail in chapter 6. So I'm just trying to introduce the concepts to you now. So these are datum feature symbol applications. Here's how we would put on a drawing what the datum feature, how the datum feature is defined. So in this case, I have a flatness tolerance of 10 thousandths applied to this upper surface, and then I put this filled in triangle here with a square or rectangular box here with a letter in it. What that denotes is that this upper surface of this part is datum A. Or I can attach that triangle here, that filled in triangle, right to the datum itself, and then this surface here is now defined as datum B. That's in a model definition. Now, if I'm applying it to a surface on a drawing, I can do it several ways. I can put the filled in triangle right on the surface. I can have an extension line and then apply the filled in triangle right to that extension line. So I can do it with applied to the surface, applied to the extension line, or applied to a geometric tolerance that defines that surface. Those are the ways I can do that. Now I want to talk about target symbols. Again, this is an introduction. We're going to talk about targets and how to use datum targets throughout this course. It's used to identify a datum target. Okay, in the last we had datum features here. Over here we're going to talk about datum targets. And then here's how a datum target is applied. There's three kinds. There is a point, a line, and an area. And then we use a circle, and that circle is split in half. This is just talking about the size. These two X's here, those are the sizes of these datums relative to your text size. Now that's something we're really not going to be talking about in this class. If I'm asking you to apply something, to a drawing. It's usually in the study guides, so it's not something. And usually your software would take care of this, because you're going to be using CAD software to create drawings. And when you use CAD software, usually, when you type in these features, it usually takes the text size and it usually does this for you automatically. So a lot of things in the textbook that talk about text size or size of the symbology, that's something you're really not going to have to worry about. And then basic dimensions. Basic dimensions establish the theoretically perfect location. A tolerance associated with the dimension is specified in the feature control frame, and then we put a rectangle around that dimension. So a basic dimension always has a rectangle, and it is a theoretically perfect dimension or location. Then the tolerance in the feature control frame is associated with the tolerance of that dimension. Okay, this is the end of Unit Chapter 2.